All right. Okay. So today we will talk about stoichiometry, and stoichiometry is very important for chemical reactions, or to understand or study chemical reactions, and also to investigate the product that will be formed during that reaction or as a result of that reaction. So stoichiometry is very important. But uh, as much as it is very heavy, the name is so heavy, we can simplify it in just a very simple way. I'm going there, but uh, before that, let's go and see what is the learning outcome for us for this from this lecture class. What do you want to study? Okay, so we will try to understand, or we will learn the balanced equation, okay? How to do the balancing of the equation. First, if we do not do the balancing, we will not know how much of that product and reactant was needed for that reaction to occur. So balancing is important. And here comes the stoichiometry. Stoichiometry is a very hard, heavier term to simply say that the ratio, okay, or the balanced amount that will require for the reaction to go to completion. All right, so this is the stoichiometry, the ratio between the reactant. When we add two reactants, one and one reactant, how much of A, let's say A and B, two reactant, how much of that reactant A will take, or B will take up A for that reaction to occur. That is called the stoichiometry ratio. And since there is A will take some, the ratio, there is a ratio between them, we can also find out which one is the excess reagent or reactant and which one is the limiting reactant, right? I mean, if we have equal ratio, both of the reactants, then the product is going to form and there is nothing left over. But if there is not enough for any of the reactants, then the reaction will not go for the completion, and there will be an excess reactant, and there is not excess is the limiting reactant. We're going to talk about it more. And also after that, we'll try to understand the gravimetric analysis for this, how to do the investigation for to understand how much of the composition or purity of the compound. So now at the beginning, let's go and see what is the chemical types of chemical reactions. Well, chemical reactions we can divide in two forms. Other forms as well, but in a very broad form, we can divide into two. That is oxidation reduction reaction, okay, and the oxidation state changes. All right, the oxidation state, that is the charge state of a metal, will be changed. It will either increase or decrease. That is the oxidation or a reduction state, a reaction. We will not talk about more about the oxidation reduction state, but a reaction, but more about the type of the reaction that holds or under the oxidation reduction. So under the oxidation reduction reaction, there are combination, right? That is two reactant when they form the reaction, do the reaction, they become combined, right? So that is the combination reaction. Decomposition reaction, that is just the opposite of the combination reaction. This combination reaction is going to be one or combined from many reactant. Decomposition reaction is from one type of chemical, it is going to be many types of product is going to be formed. Single displacement reaction. Single displacement, like here A, B, and C, or AB is shown as a reactant. For a single displacement reaction, AB is one single component, or it is one type of chemical, and C is different type of chemical, and these two becomes and forms doing the these two are doing the reaction. So the C is replacing someone from this AB. So in this case, it is shown that B has been replaced and C is coming into that place. So this is called the single displacement reaction. All right. Okay, Pro, to ask you, do you have any question? If you have any question, you can just ask anytime. Okay, just unmute yourself and then ask the question. All right. So now we go and see more into that examples of these different type of reaction, combination reactions. Like for this case, aluminium and oxygen, right? Aluminium and oxygen, they combine together and produces aluminium oxide. But in this case, if you see that 2 aluminium here and 3 oxygen molecules were involved. Here it is, if I just put 1 aluminium and 1 oxygen, nothing is not going to produce aluminium oxide, because from here, when we see that the aluminium here, that means 2 aluminium means 2 aluminium molecules. In this case, it's atom, but usually it is 2. So these 2 and these 2 for oxygen are not same, right? These 2 and these 2 are not same. These 2 for representing the atoms. It's representing the atom. For this case, we see that here is 2. That means 2 molecules of lead nitrate. 2 molecules of lead nitrate. I mean, all things, lead and nitrate is there, and also 2 there. But these 2 here for this nitrate means there are only 2 NO3 are there. 2 NO3 there, but not 2 Pb there, right? So these 2 and these 2 are different. This means that the 2 moles, 2 molecules are involved. So here it goes for combination reaction. A plus B is forming AB, and aluminium, 2 aluminium molecule. In this case, aluminium is atom, because aluminium molecule and atom is, for this case, is same. So here 3 molecules of oxygen. Okay, 3 molecules of oxygen is attached to 2 moles of aluminium, and in these 3 molecules of oxygen, there are 6 oxygen atoms, because 3 times 2 will be 6. So 6 atoms, oxygen atoms, are involved in this reaction. So in another way, we can say that 2 moles of aluminium and 3 moles of oxygen are involved in this reaction and is producing 1 mole. Here there is only 1, right? Since there is only 1, we don't need to write it. So since 1 mole of aluminium oxide are produced from this reaction. So this is combination, because there were aluminium and oxygen, and then it produces aluminium oxide only from 2 different species, or 2 different molecule. 1 single type of molecule is produced. That is, aluminium was solid, oxygen was gas, and aluminium oxide, which is solid, is also produced. So it will have, aluminium oxide will have different property than aluminium itself or oxygen itself, right? So this is why it is combination reaction. Decomposition reaction is just the opposite of combination reaction. And in this case, lead nitrate was decomposed or broken down to smaller parts. So in this case, 2 moles of lead nitrate, 2 moles of lead nitrate produced 2 moles of lead oxide and 4 moles of nitrogen dioxide and 1 mole of oxygen gas. Okay, so this is the decomposition. It just breaks out in smaller parts. Single displacement reaction, magnesium and 1 mole of magnesium, solid, magnesium is metal, and 2 moles of HCl were engaged in this reaction, and magnesium chloride formed. So this magnesium replaced the hydrogen from this HCl, and hydrogen was expelled. So this is the single replacement reaction. So this is the balancing. This is how we should be balancing the reaction, because if we do not balance here for again I'm going to the combination reaction A. That's if we do not balance this reaction 2 and 3, we just leave it like aluminium and oxygen, it will be wrong. It will not be an aluminium oxide. We have to provide a specific or a certain ratio of all those reactants. Only then the reaction is going to produce the product. So the same goes for this decomposition reaction as well. 2 moles of is producing, and then we have to make sure that in both sides, right, reactant and product, both sides, they are going to have exact amount of all those elements, exact amount of atoms of in all those elements. So here 2 aluminium, here is 2 aluminium as well. Here is 6 atoms, right? Oxygen. Here is 3 as well. Here, I mean, it's converted to 3 as well. And for this lead nitrate, 2 lead nitrate was is going to produce 2 lead oxide, and we have to make sure that here is a nitrogen and oxygen and lead. All of these are in equal amount in both sides, in both cases. Okay, so this is the balancing of equation. So now,
excuse me, sir.
yes.
In the combination reaction, what happened to the other oxygen?
Yeah, this is the thing that here 2 aluminium and 3 oxygen. So it should be here should be 2, and here it will be 4. Thank you very much.
All right. Thank you.
Thank you. Here it is deliberately given, so thank you for speaking up. Anyway, so if you see any mistake here, so please speak up. So it will be 4 here, only then it will be balanced, right? If we put 2 here in this side, it will be balanced, right? Okay, so thank you for that. And stoichiometry. Okay, so what is stoichiometry then? In a very, simple sense, stoichiometry is the ratio. Like, okay, go there. Stoichiometry is the ratio and relationship between the mole ratio of the reactant, different reactant that is going to do reaction. In a simple sense, so if we say that there are a lot of examples that I can give, but just keep simple that when we are going to boil something, right? I assume that many of you have the same experience of boiling, if not cooking. So if we are going to boil it, if we put less water, what will happen? The things will not get boiled, right? So it will become burnt. Or if we put too much of water, the thing will be dissolved in the water. Or if it is not dissolved, it will be boiled and the water will be waste. It's just a waste. So this is the thing. This is the, stoichiometry. It tells us how much exactly I need to use the reactant so that it is not excess or it is not the, limiting, deficient. So to get the maximum product, we need to find out what is the stoichiometry for this. If we do not balance the reaction, stoichiometry is balancing the reaction. If we do not balance the reaction, we will not know. Just like this, the combination reaction. If we do not balance this reaction, we will not know how much aluminium we are going to use it here. If we put 2, it is not going to work, right? Okay, so for first example, it is a little advanced example, but it is better to start with the advanced example. Like example 1, we all have this experience of airbag. Not experience, but we know that the airbag is installed in the car and it saves life. But what happens when this accident happens. So the collision happens. When the collision happens, there is a chemical trigger, and this triggers this airbag to inflate. It must be inflated by 0.04 second, even less than a blink of an eye. So, but it should be not more than 67 liter of nitrogen gas. Okay, if it is, why the stoichiometry is so important. If it is more than 67 liter, like it's 70 liter, let's say it's a 70 liter, it will give so much pressure on us that we will get injured. It will not save us, but it will make us injured. Or if it is less than 67 liter, it will not save us anymore. It will fail to save us. So we need exactly 87, 67, 68, 69, not more than, not too much. So if we get, to make sure that we get around 67 or 67.5 liter of nitrogen gas, how much of sodium azide should we be using? And from this reaction, if we do not put 2 in front, right? If we don't put 2 in front, we just write sodium azide, we will get sodium and nitrogen. But that does not tell us how much or nitrogen gas is going to be produced from this sodium azide. Once we balance this equation, we put 2 here, 2 there, and 3 here, then we only know that from 2 moles of sodium azide, I will get 3 moles of nitrogen gas. And when I get the 3 moles of nitrogen gas, right, we can find out what is the liter or mass of that gas. And I hope that you have gone through the formulas that was given in the first lecture. At the end of the first lecture, the gas and number of moles and all those things, it will be handy, it will be needed today to understand this. Okay, so now it says that calculate the mass of sodium azide needed to produce enough gas at 300 degrees centigrade and 101 kilopascal, that is almost 1 atmosphere. On 1 atmospheric pressure, that is the normal pressure on the sea level. So that is, we have to find out that how much of that sodium azide I should be using to get like 67 liter of sodium nitrogen gas at 300 degrees centigrade. We have to remember that at 300 degrees, it is not asking us at the room temperature, but at 300 degrees centigrade and 101 kilopascal, okay, or 1 atmospheric pressure. So what we will do is, we know already that this is the stoichiometric ratio is 2:2:3, or for us here it is a more important thing because we are looking for nitrogen gas production, so it is 2:3. If I use 2 moles of sodium azide, I will get 3 moles of nitrogen gas, right? So from here we see that from 2 moles, 3 moles, and then we do this balancing in this way that it becomes 2 moles of 2 moles of sodium azide will produce 3 moles of nitrogen gas. And then another thing is we need to find out that how many gram it will be required to produce 67 liter. So here there is 2 different things that it is, the condition is telling that I need in liter, all right, 67 liter, but the condition is asking that find out in gram. So there are 2 different units is used here, and 2 different units are not at the room temperature. Like gram is always gram. Whatever temperature is always gram, but the liter will be different in different temperature and pressure. So this is one critical thing. We should be aware of that. So now the first thing that is asking that we should know this 67 liter of nitrogen gas at 300 degrees centigrade and 101 kilopascal, and it is producing from this reaction we already have seen. So mass of, so from there we know that N equals PV RT, all right, or PV equals to nRT. From there we find the number of moles of nitrogen gas is how many. We have at this temperature and pressure, how many moles of nitrogen gas is being produced if it is 67 liter. Okay, if it is 67 liter, how many moles of nitrogen gas is going to be there? And from there we find that if is 2:3 ratio of nitrogen and sodium azide, okay, nitrogen and sodium is 2:3 ratio. That means if 1.42 moles of nitrogen gas, that means how many moles of sodium azide. So from there, sodium azide we find is 0.947 mole, and afterwards we see that sodium azide, from their number of moles is, if we just multiply with the number of moles with the molecular weight, we will find the gram. So mole and 0.947 moles times 65.052 gram of sodium azide is the molecular weight of sodium azide. So from here we see 61.57 gram of sodium azide will be required. Here in mole and mole will be cancelled out. So this is what is left over. The gram is only left. All right, so this is one of the very interesting and important example of stoichiometry, how stoichiometry is doing, or how stoichiometry is helping us to find out the amount, right, of product or reactant. It can go backward as well, that I know already that I have 62 gram of sodium azide is there. How many liter of sodium so nitrogen gas can be produced? So it will go backward, and we will use the same limiting reactant and excess reactant, and also we'll find this number of moles and PV and RT in this way. So there are another type of chemical reactions that is called a double displacement. Okay, so in double displacement there is a precipitation reaction, that is two solution, a different type of solution will be involved, and at the end we will get the precipitation. That means precipitation is the solid at the end of the reaction, when there is something solid occurs. Okay, at the in the test tube we mix 2 or 3 different type of chemicals, all are in liquid form, and at the end we get something solid that does not dissolve in that solution. So we can filter it out, we can weigh it, so that is called the precipitation. So this precipitation is can be in double displacement reaction. Another one is, of course, acid and base reaction. That is acid and base always produces salt and water, so that is the double displacement reaction. So for reaction, okay, different type of reaction, we need to before balancing or before going to the stoichiometry, or one of the very important aspect of doing the stoichiometry is able to write the equation. If we cannot write the equation, molecular equation or ionic equation, then of course there is no condition of balancing it out. So the first thing is we must be able to write the reaction, and there are 2 ways to write the reaction. One is the molecular reaction, equation, and another one is ionic equation. So ionic equation the first thing here, you see that acid-base reaction, it is only shown that hydrogen plus and hydroxyl, right? We do not know this hydrogen is coming from where and hydroxyl is coming from exactly where. Is sodium hydroxide or potassium hydroxide? It is HCl or HNO3, but only this H and OH is being shown. So this is called the ionic equation. H and OH in the ionic form is called the ionic equation. So the writing of the ionic equation, of course, before ionic equation is important so that we can find out what are the main ions that are involved in the reaction and which are causing the reaction for this precipitate to occur or the product to occur, and also the ionic the ions I forgot what I wanted to say. Okay, so the ionic equations are it tells us that what of the ions are actually doing the reaction or actually involved in those reactions. So first of all, we have to, of course, we have to write the molecular equation. If we do not write the molecular equation, there is no way we can write the ionic equations or molecular equations. So we have to write it first, and then we have to balance the equation. Otherwise, there will be a mistake that we do not know how many of the ions are produced if we do not do the balancing. Then we have to write down the small aqueous species as a separate ion. The aqueous one, the ions are actually, we are writing if there is a gas or liquid or solid, the ions are, we are not showing it as an ion, because in a solid form, they are in solid, they are not in ionic form. Only those are in aqueous form, those are in ionic form, ionic state. They are only in the ionic state. Okay, and then we have to write out the ionic equation after we cancel the common ions or spectator ions that do not take part in the formation of solid or liquid or gas. So acid-base reactions, this is double displacement, and we see that calcium carbonate and hydrogen chloride, right? Calcium carbonate and hydrogen chloride, they are reacting together and forming a calcium chloride, water, and carbon dioxide gas. Okay, so this is calcium chloride, mean AQ means they are in aqueous form. That means they are dissolved in water. Aqueous is water, so they are dissolved in water, and they are in liquid state, or how do I say that? They are in water, so they are in the solution. But H2O, that is already becomes water. Okay, that is already becomes water, so it is in liquid. It is not in aqueous, it is in liquid. Carbon dioxide, that is gas, the bubble of carbon dioxide go out from the reaction, so it is in gaseous form. So now when we write the ionic equation, first we need to balance out the equation. Here we see there are two chlorine or chloride ion here, and here is only one chloride, right? The atoms, two chloride atom here, and ions here, and here is only one chloride, HCl, because there is only one in front, so only one, okay? One hydrogen, one chloride. But here we see that one calcium, but two chloride. So there is a deficiency of chlorine for this side, because if there is not in this side, where it is coming from? So what we'll have to do, and there is two hydrogen in this side as well before the oxygen. So what we'll do is, if we put 2 in front of HCl like this, now it is balanced. The whole equation is balanced because there is everything is same on the both sides. So here we see that calcium carbonate 2 hydrogen chloride, calcium chloride, water, and now we'll only the aqueous species we will write in ionic form. On the reactant side, calcium carbonate is solid, right? It is in solid form. S means solid. So that means they are not in ionic form. They are not ionic. They are still in the solid. They are sitting down in the, let's say, under the test table, they are sitting down. And HCl in aqueous form. That means HCl already mixed with water and then it is in a solution form. We cannot differentiate water and HCl in that solution. So this is an aqueous form, and in aqueous form they are also only ionic. So hydrogen, 2 hydrogen, because they have 2 hydrogen and 2 chloride ion are shown. Hydrogen is positive charge, chlorine is negatively charged, because this is non-metal, right? Hydrogen is, I mean, different thing, because hydrogen always positive. Okay, just remember it. So here calcium in aqueous, calcium chloride is in aqueous form. So calcium, there are 2 positively charged, because calcium is a metal, and it is also in the okay, calcium is negatively positively charged, 2 positive charge, and then chloride is negatively charged, so it is 1 negative charge. So it will take 2 chloride to neutralize this 2 charge. 2 times 1 is 2. So and calcium has 2 positive charge. So 2 negative charge of chlorine, 2 negative charge of chlorine will neutralize. Okay, 1 from here, 1 from there. So 2 will neutralize 2 positively charged. Okay. Water is liquid, so we do not write in aqueous, I mean ionic form, because in what, I mean liquid form, water in liquid form is very small amount of it is liquid, ionic. Mostly is not ionic, so we can just very small, I mean insignificant, so can ignore it. And carbon dioxide, when it is in gas form, we do not need to mention it as in aqueous form, because they in ionic form, because they are not in ionic form, they are in molecular form. So cancel, from here we see that chlorine on the both side, right? Chlorine on the both side are the same, 2 positive negatively charged chlorine, and also here 2 negatively charged chlorine, and this is called the spectator ion. I mean, it has not been changed. It was same like in reactant and product, they are the same. So we can just cancel out this thing, no need to consider that, because the reaction did not happen in that way. So the reaction is happening is calcium carbonate and hydrogen ion. So calcium, and this is the net ionic reaction. So the spectator ions are left, out. The spectator ions are not considered. Question number 3, any question? Is there any question? Okay, so if no question, then okay, let me see. So when writing the equation, do we have to write out the state of matter for each reactant? And yes, if it says that write the ionic equation, then of course you have to write out the state of the reactant and product. Most of the time we do not need, but sometimes it is required. If it is required, but it is better, it is a good practice to write the state of the matter for both reactant and product. This is a good practice. Okay, is there any other? Okay, let me see. I think the equation for the combination is not balanced. Okay, thank you. Yes, if any question, just ask me. Now we are going to the example 3, right? So 1 gram, it says that 1 gram of calcium carbonate before that, I want to show you one thing. The periodic table. I want to show you the periodic table. Okay. Just hold on for a moment. Okay, here. So, yes. So here, number, this is the group, and this is the period, right? So 1, 2, 3, 4, 5, 6, 7, 8. This is the period, and 1, 2, 6. This is the period. So group. Sorry. So here, number one, group in one first group, all of them, hydrogen, lithium, sodium, potassium, all of them has positive 1 charge. Second group, beryllium, magnesium, calcium, all of them has 2 positive charge. So in 13, or previously it was group 3, so 13, all of them has 3 positively charged. Okay, and then here 14, they have 4, and so on, 5, 6, 7, and neon, or this is the noble gas, so it does not, ideal gas, it does not have any charge. They do not carry any charge, right? So 1 positive charge, 2 positive charge, and then 3, 4, and for non-metal, those are the non-metal, they will have a negative charge, right? A fluorine, oxygen, chlorine, bromine, they will all have negative charge. But these are the transition metal, all right? These are the transition, come on. These are the transition metals, right, in the reddish color. So they are, however, have different oxidation state. It's called oxidation state. So they can have positive 1 to positive until positive 7. So one of them, any of them, can has different, many, not only one. Like one, group 1 and group 2, they have only, group 1 has always positive 1, group 2 has always positive 2. But for this transition element, all of them has multiple charges, or oxidation state it's called, that like for iron or cobalt, let's say, and electrons, right? So let's go and check iron. And it has oxidation state -2, -1, +1, 2, 3. 2, 3 at the predominant. So let's say it's 2, 3. Okay, even it can reach up to 6. So 2, 3 is iron 2, iron 3. We always, I mean, I think that you have heard iron 2, iron 3. For copper also, it has +1 charge, +2 charge as well. We can see sometimes. So zinc also has +1, +2, mostly 2, but it also can go +1, +2. So these, and they are the metals, all of them are metals. So these are the metal, the transition metals. It's called transition metals, so it is the metal. So they, all of them has positive, multiple different type of positive, not only one, many positive charges. So this is I wanted to show. And another thing, okay, another thing is, from this periodic table, we can find out the molecular atomic mass, right? For hydrogen it is 1, right? For beryllium it is 9. Here at the bottom of the beryllium is 9.012. So this is the atomic mass. And oxygen has 15.99 or 16 atomic mass, and iron has 55.85. So these are all these atomic mass at the bottom of them. On top of them, this is 1, 3, for hydrogen is 1, lithium 3, beryllium is 4. These are the number of protons, right? Number of protons they have. Okay, so now again going back to our lecture slide. Where is it? All right. So we are going, we were here that 1 gram of calcium carbonate, example 3, is another example 3, example for balancing out the reaction first, and also to find out the, use the PVNRT, the gas volume, gas law, sorry, the gas law to find out the number of volume, the amount or the volume of the gas. So here he says that 1 gram of calcium carbonate reacts with 250 milliliter or 0.1 molar ACl according to the reaction below. Calculate the volume of carbon dioxide gas released at SLC. There are two things. Please, please take note that it says 1 gram of calcium carbonate, right? It's 1 gram of calcium carbonate, but it says that it's 250 milliliter of 0.1 molar aqueous ACl. So there are two different units. Again, it has been used here. 250 milliliter ACl, 1 gram. Two different units. Now I have to write out the equation first and have to balance, otherwise I cannot understand that how much of calcium carbonate or HCl has been needed, right? And this reaction is already balanced out in this. Luckily, if it was not balanced, first thing we had to do is to balance the equation first, right? Balance the equation first, and only then we can go for the calculation part. So we did the balancing, and it was balanced actually, and it says that 1 gram of calcium carbonate and 250 milliliter 0.1 molar ACl, right? So how many liter of calcium carbon dioxide, sorry, will be produced? Different what do you call it, units has been used. So it's tricky thing. Do not be tricked. So just think that I have always need to, does not matter how many kg, how many gram, how many liter, how many volume of the reactant are being involved in this reaction. All these things needed is the number of moles, right? The number of moles. The first thing we have to find out the number of moles for the reaction that is happening here. So calcium carbonate is 1 gram. First thing I have to do is how many moles? HCl is 250 milliliter, and 1 molar in 250 milliliter. Okay, in 250 milliliter of 0.1 molar, how many moles of HCl are there? I have to find out this thing, and only then I will find what is the limiting reactant or what is the excess reactant, or will this reaction really occur or not, right? So from here, after we find out, we can go for the number of mole, the liter of carbon dioxide that is be produced. We can only go then, not now, right now. So what we'll do is we will find the number of moles, and we all can see from the balanced equation that it is 1:2 reaction, right? So if there is 1 mole of calcium carbonate, it will take 2 moles of HCl, right? It will take 2 moles of HCl to react with 1 mole of calcium carbonate, right? So let's see, we do not assume which one is limiting or which one is excess. We just calculate first. 1 gram of calcium carbonate, and calcium carbonate, the molecular weight of calcium carbonate is 100. How do we do it? 100, because calcium is 40, right? I'm sure that you know how to, but in any case, in case anybody are not sure, so calcium is 40 gram per mole. I'm not writing it here. how do I know it? I got it from the periodic table. Just now I showed the periodic table, right? So from there I see that it is 40, around 40. We can just round off to 40. The calcium is 40, carbon is 12. Carbon is 12 gram per mole. And oxygen, there are 3 oxygen atoms involved, and each of them is 16. From the periodic table, I see 16. Oh, I cannot delete it. Okay, 16 times 3, right? And now I add up all those things, all those numbers. So 16 times 3, 48 plus 12 plus 40 is equal to 100, right? Gram per mole. This is gram per mole. So this is the molecular weight for calcium carbonate. And HCl is 250. So now the molecular weight of calcium carbonate, so how many mole in 1 gram? So mole over mole, gram per mole is 1 over 100. This is the molecular weight. So I divide number of moles. This is the formula. I think it was given in the previous, at the end of the last lecture. I hope that you have seen it. So 1 over 100, that means the number of moles that we already found it, right? The number of moles we already have found. And then the NaCl, number of moles for HCl is in 200, it is in milliliter, right? So I have to convert into liter first, because this molarity is moles per liter. Sorry, this is moles per liter. Moles per liter. So if I multiply it with liter, then this liter will cancel out, only the mole will be left out. So from there we will find how many number of moles for HCl is there. So I have to convert it from this 250 milliliter to liter first. How do I convert it? I divide it by the liter. If I divide it by liter, I will find it if I divide it by 1000, I will find the liter. It will be converted to liter. 250 over 1000 is the in liter times this concentration, moles per liter. So from there we find this is the number of moles in HCl. All right. So we find the number of moles of calcium carbonate and number of moles of HCl also. And it is good that we are all set, right? Not yet. We have to find the limiting reactant. Afterwards, after we find the number of moles, we have to find the limiting reactant. All right. We have to see how, because we see that 1 mole, because here in before calcium carbonate there is 1, right? That's and here is 2, right? So and before this carbon dioxide there is 1. That means 1 mole of calcium carbonate and 2 moles of HCl is producing 1 mole of carbon dioxide. And we need to see whether this whole number of moles, that means this is the number of moles, will produce exact amount of carbon dioxide or not. Whether this is the, this reaction will go all the way until it finishes 0.01 mole of calcium carbonate, or it stops before that. How does it stops before that? If it is a limiting reactant, then it will finish up first, right? If it is an excess reactant, if calcium carbonate is the excess one, then HCl will finish up first, and then the reaction will not be completed. So we have to find out which one is the limiting reactant. So from there, we find out that here is that we divide by the stoichiometric ratio, because here is only one we see. So we find that calcium carbonate divided by the stoichiometric ratio, the one in front of it, it has 0.01, of course, but 0.025 divided by these two, the stoichiometric ratio it has divided by 2 is 0.0125, right? Still it is more than this. So this one is more. HCl number of moles is more than the number of moles of calcium carbonate. That means HCl is the excess reagent, and this is the limiting reactant, okay, or reagent. So if it is the limiting reagent, that is good, that it will finish up faster. It will finish up faster, and then there will be some leftover of HCl in the solution. So when it will finish up faster, that means it is, carbon dioxide is going to follow the mole ratio of this limiting reactant. The product is going to follow the mole ratio or number of moles of the limiting reactant. So since 1 mole produces 1 mole of carbon dioxide, and 0.01 mole of calcium carbonate will produce 0.01 mole of sodium carbon dioxide as well. And this we found out that it will produce 0.01 mole of carbon dioxide. So the carbon dioxide, number of moles of carbon dioxide, we can find from this molar volume, that V over Vm, that is the volume over molar volume is the number of moles for any gas. Okay, it is the formula for any gas, that to find out the number of moles of a gas, if we divide the volume of the gas by the molar volume of that gas, we can find the number of moles of that gas. But there is one thing to consider, that this Vm, the molar volume is dependent on the condition. If it is an STP or SLC, that is standard laboratory condition, the molar volume is 24.5. Okay, if it is an STP, that means standard temperature and pressure, all right, so the molar volume Vm will be 22.4, right, 22.4 liter per mole, just like this, liter per mole. So since it says that the problem says that find out the molar volume into at SLC, so I divide it by 24.5. If the problem would ask me that find out the volume at STP, not SLC, then I have to divide it by 22.4. Okay, so this is one thing that I think you should take note at. Okay, so this is what I was just telling you just now. Another example for precipitation. When there is a precipitation, when are there a precipitation? When the product does not get dissolved in the solution that is produced, or the mixture. So for this, we see that we have to write the net ionic equation. We can also write the molecular equation, but if we write the molecular equation, it does not give us the information of what ions were involved in that particular production of that particular solid, or the precipitation. In the molecular reaction, we cannot find it, but from ionic reaction, we can find it. So first of all, of course, we have to balance the equation. And balancing the equation shows that only if I add 2 in front of the sodium chloride, the reaction is already balanced. Sometimes it can be very tricky, yeah? So try to learn how to do the balancing of the equation. And afterwards, we will write the ionic form of the species that are in aqueous form, right? Those are in aqueous form. For here, we see the sodium sulfate, Na2SO4. Okay, why Na2? Because as I said, that sodium is group 1 element at the very left side of the periodic table, group 1. So it is always 1 positive. But SO4, the sulfate ion, has 2 negative charge on it. So to neutralize that 2 negative charge, 2 sodium is needed. So each sodium will contribute 1 charge, and then 2 sodium contributes 2 positive charge, and that neutralize the 2 negative charge on sulfate. Same goes for beryllium chloride. Beryllium bears or carry 2 positive charge, and chloride ion 1 positive charge. So 2 chloride ion neutralize the 1 beryllium charge. Okay. So sodium, so those are in aqueous form. Those are in aqueous form. We will write the ionic form of those species, or of the ions. So sodium, sulfate, beryllium, and chloride all are in aqueous form, so all of them. And here on this side, only sodium chloride, because sodium chloride, of course, they are salt. All of them are actually salt. So they will be in aqueous. Salt are always aqueous. And they will, electrolytes. Okay, so they will form aqueous solution, so that we write all those in aqueous form or in ionic form. And those ions that are not participating in any kind of reaction, right, or in both reactant and product side, they are same, so that we just cancel out them. So sodium, I see that sodium and chlorine, they are not taking participation on both sides. They are the same. Only barium and sulfate ion, right? They are not found on the product side in the solution. So this is the net ionic equation. We cancel out the spectator ions and leave out with this. So high solubility and low solubility, there is a set of ions that will produce high soluble compound, and there is others that will not produce them. Here are the list of those: sodium, potassium, ammonium nitrate, acetate, chlorine, chloride, bromide, iodide. Those sulfide, those are very high soluble in it. There are, of course, exception. There are exception in both sides. So, and the low solubility are those who are not having those sodium, potassium, ammonium, or carbonate, phosphate, or hydroxyl. So these are the low soluble. There is a set of ions or charges that produces high and low solubility. But this is just a simple glimpse of it. There are exceptions. There are much more about it to learn when we go for higher class or degree. Okay, so this is not all. This is just introduction. Now we go for this. Using these type of techniques, the reactions, all right, or finding out the limiting reactant, or finding out this excess reactant. How can we use this reaction to find out, to do some investigation, or find out the unknown amount or unknown compounds, right? So this is the thing. This is the way of doing the analytical technique. So in analytical technique, right, there are two branches of analytics. One is weight chemistry. Weight chemistry actually that involves in the reaction, right? Involved in the reaction that can be gravimetric reaction, that can be volumetric reaction as well. And the other branch is instruments or instrument. I mean, using the instrument. Instrument is very simple thing. You just put the sample there. The instrument is going to tell you the result. But depends on what type of sample or what the outcome you want. There are different instruments are used. We'll see some of the chromatography and spectroscopy later on, so we will know more about it. But first, let's go to the weight chemistry. That is the technique. That is weight chemistry because it involves the solution. So weight chemistry, that one of them is gravimetry. Another branch is volumetric solution. So the gravimetry actually is by using the percent composition or to find out the precipitate, from that precipitate to find the total ion in the precipitate. That is the gravimetric analysis. So in gravimetric analysis, this the sequence is we weigh the sample, we form the precipitation, we infuse or introduce the precipitation to occur, and then when the precipitation occurs, the precipitation is filtered out, and then it is dried. Different ways we can dry it, and then again we weigh the precipitate. So how much of the solution we took and how much precipitation from that solution we found, we compare these two, and then from there we find out the material or the components inside. So when we are saying that we do the precipitation, you already know that the precipitation should be known precipitate, right? It should be known precipitate. All right, it should be known precipitate. Otherwise is something wrong. I mean, unknown precipitate, we do not know what is the unknown precipitate. So we will never be able to find out that what happened there if we do not know what the precipitation occurred, right? So the important thing is we must know what are the precipitation or what is the precipitate formed of. So that is why we should know that the known precipitates are silver chloride, silver bromide, silver iodide, and this is not the all, but this is just a fraction of the different precipitate that we should be targeting for, because we know the molecular weight of them, we know the charges of them, and we know how much it can form from how much of the reactant they use. Okay, just I need to put my laptop on charge. The charge is going to finish first. So the precipitation, there are some rules that it must have some known formula. We know the formula, and then the solubility. It should not be, after it becomes formed precipitate, it should not be dissolved again. That is important thing. Stable, it should be stable on the heat, because if it is a very volatile, and then after the precipitation occur and we go to measure it or heat it to dry, it will be gone. So it cannot be used. And those are things. Okay, so another example for gravimetric example, we use it to find out the salt in the chips, right? Lay's chips, yeah, the potato chips, because they use a lot of salt in it, and salt is quite an issue for health. Those who are hypertension, high blood pressure, that is very problematic, dangerous for them. So we want to find out how much salt, not only Lay's, but others as well, this type of potato chips, or any other food, let's say other food, we want to know how much salt or sugar in that some cases, we can find out how much it can produce or it contains. So what we'll do is, since the salt is sodium chloride, right? So silver nitrate solution was used to produce silver chloride, and silver chloride, just from this, you see the silver chloride here, it is a precipitation, or it's a precipitate, and it does not get dissolved, and it is solid. And we know the formula of it, we know the molecular weight of it. So silver nitrate was, and we also know silver nitrate. So silver nitrate was used to precipitate out the silver chloride, and the silver chloride mass was found to be 0.122 gram. Okay, after this 5.4 gram of chips, we dissolved it, and then we used the silver nitrate, and from there we found 0.122. So the thing is, 5.4 gram, this 5.4 gram is not the sodium chloride, but it is the chips. It got many things inside. One of the things is sodium chloride, and only the sodium chloride will form the silver chloride precipitate. The other things will not. So from there we found 0.122 gram of the precipitation. Right? So if 0.122 gram of precipitation, that means silver chloride, is formed, how much do I have, or in these chips, how much sodium chloride is there? So it will not be, clear for us unless we write the equation. When we see that sodium chloride plus silver nitrate, sorry, and then it is producing silver chloride, then it will be much more easier for us to understand. So this is the salt that we eat, and sodium nitrate was used. How do I delete it? Okay, so sodium nitrate was used to, silver nitrate was used to create the precipitation and make the precipitation, and silver chloride was the precipitation, or this is the solid thing, and along with it sodium nitrate was formed, but we are not interested in sodium nitrate. So from here we see the ionic reaction. From this molecular reaction to we produce the net ionic reaction. From here we see, after we deduct the spectator ion, we see that here there are chlorine and silver together, they are producing silver chloride, right? And this silver chloride, according to this problem, it is 0.122 gram. Right, and 5.4 gram of potato chips were used from here. So how many gram or sodium chloride would be there in 5.4 gram potato chips? And if we can find out, we can find out easily how many gram of sodium chloride in 100 gram or 1 kg or how whatever of potato chips will be there. So the thing, first of all, we have to find, because mass to moles, because here, can you guess the pathway? You already have the slides, but can you guess the pathway? Where should we, how do we find out the number of moles or mass of the sodium chloride, right? So here we see again number of moles, right? Number of moles 1, 1, 1. Right, so here it is, we are lucky that everything is 1, 1, 1. We don't need to balance it, the reaction is already balanced. So 1 mole of silver chloride is produced from 1 mole of silver nitrate or 1 mole of sodium chloride. So we need to find out how many moles of silver nitrate was used, and then or how many moles of silver chloride is being there, so that we know that exact amount of sodium chloride, number of moles of sodium chloride are there. So from here we see that number of silver chloride and number of moles of sodium chloride is 1:1. So the number of moles are same, right? Number of moles is same. If in case it was 2, like, I mean, just for an example, if it were 2 and it was 1, then it would be 1/2, right? It would be 1/2 of this, because it would be 1/2 of these two. So in this case, I'm just telling that it can happen. Not everything is very easy, right? Not always. So yeah. So we find that number of moles of sodium chloride is also exactly same, because this ratio is 1:1. Ratio is 1:1. So from there, it is so easy to find the mass of sodium hydroxide, because you just multiply with the molecular weight of sodium chloride, and then we find the mass of sodium chloride. Okay. Now, percent by mass. So the mass that we find, the sodium chloride 0.0498 or 0.05, if we round up to, it will be in 5.4 gram. It was in 5.4 gram, because we started with 5.4 gram of these chips. So if it is in 5.4 gram, then in 100 gram or 100% is what? So it in 100% it is 9.923 gram, or in 100 gram, or 0.923% of sodium chloride is used in that chips. Finding the percent yield. So what is the percent yield? It is how many percent of the product will be produced. That is the percent yield. Can you excuse me? This point is bothering me. Hold on. Okay, so percent yield means, okay, just I said that percent yield means how much yield, or the product, percentage of the product has been produced in relation to that of the ideal production. All right, so before that we see that the reaction, all the reaction is very hard to get more than 100. We cannot find more than 100% of the product. First of all, this first thing, that we cannot make more than 100% product. 101% product, no, it cannot be. We cannot make more than that. First of all, this is because of the natures of rule. Another thing is, what is that? Oh, another thing is that since there is not 100%, it is always, mostly, it is less than 100%. The product is always, most of the time, 99% times, it is less than 100%. The product will be formed. Rarely it is 100%. So theoretically, if we calculate the product maybe from the reactant, it will see that, okay, this much product will be produced, but in actual case, that is not the case, right? So actual case, the produced product is always less than what we can calculate from this, from what we have calculated from this product we produced. And since there is a difference between actual mass of the product produced and the theoretical mass of the product produced, it is the percentage of the actual mass produced all right, in relation to the theoretical process is called the percent of yield. It's the percent of yield. So this is, we can also find out by the gravimetric analysis the percent of yield, how much the reaction, and from that percent of yield, we can also trace back actually how much of the reaction has occurred. Although theoretically we say that all the limiting reactant will go to the product, right? But there is a gray area here. Not every time everything is produced. Okay. So actually, especially for industrial level, not every time all the products is produced. Okay. So for this, I forgot. I should remember. Just to inform you that on 9th, all right, so today is 7th, I think. Today is 7th. 9th of September at 2 p.m., 2:30 p.m., I think, there will be another talk from the water treatment. He is a chemical engineer, and he has a 20 years of experience for working here in water treatment plant. So there will be a talk. I'm sure that you will know many information about the water treatment, how the water treatment happens, and what it takes to be a water engineer, water scientist. You can attend the talk. I will share the link later on in the announcements section. Okay, let me note it down. I'll forget. Okay, so it says that calculate the percent of yield if 37 gram of lead iodide is produced from 30 gram of potassium iodide. And the reaction goes according to this, and the reaction is balanced already. It's a good thing. So what is the percentage actually has been produced of the lead iodide has been produced from lead nitride or potassium iodide. So from there we see that 2 moles of potassium iodide produces 1 mole of lead iodide, right? The ratio is 2:1. So since we are looking for potassium iodide, number of moles of potassium, it is on the numerator. It is on the numerator, right? Numerator, and this one that we know already, number of moles of potassium iodide, it will be denominator. So that, and the ratio is, this one is 1 and this is 2, so this is 1 and this is 2, right? So number of how many moles of lead iodide is going to be produced from here. From there we see that 30 gram of potassium iodide. So we can find the number of moles of potassium iodide so easily, because just divide by the gram per molecular weight of potassium iodide. That is, potassium is 39.1, iodine is 127. So that is the total gram. This is gram, 30 gram, and this is the gram per mole of potassium iodide. So this gram and gram cancelled out, only the mole left. So the total is 0.0903 moles is there. So mass of potassium iodide, right? Mass of potassium iodide is easily we can find. We can just multiply potassium iodide with its molecular weight of potassium iodide, which is 207 for the, lead iodide. 207 for lead and 127 for, there are 1 iodine, so 127 times 2. So this is the gram or mass of potassium lead iodide that is being produced from this. And now we are going to find out the percent of yield. All right, the percent of yield is, this is the theoretical mass, right? This is the theoretical 41.6 is the theoretical mass, that it is ideally this much would be produced in the reaction, this much would be produced. But from here we see that it says that 37.5 gram of lead iodide was produced. So it is not 41.6. So what is the percent of yield? How much percent actually converted in respect to that theoretical mass? So this is percent yield is actual mass by theoretical mass of product times 100%, and this is 37 only has been produced, that is only given into in the problem, and this is 41.6 that we find out from the calculation, and altogether it is 90.1%. So the percent yield for this reaction is 90.1%. The conversion can be 90.1%. Example, another example is finding the percent of purity, all right? Whether the sample is pure or not, how much, what is the purity of the sample of there. Here is the it says that the active ingredient of an antacid powder, that magnesium carbonate is the antacid that we take for our antacid purpose. When treated with excess hydrochloric acid, all right, note that it already says that it is excess hydrochloric acid. That means hydrochloric acid is excess, and magnesium carbonate, it is the limiting reactant for this limiting reactant. So a 3.5 gram sample of antacid powder, 3.5 gram sample of antacid powder produces 715 milliliter of carbon dioxide. Again, here there are different type of units are being used, right? 714 milliliter of carbon dioxide was produced from 3.50 gram of sample measured at 22 degrees centigrade and 101 kilopascal. Okay, so this milliliter in 22 degrees centigrade, 101 kilopascal. Calculate the percentage of magnesium carbonate in the powder. In 3.50 gram, there is calcium carbonate, magnesium carbonate up there already. But we do not know how much magnesium or magnesium carbonate is actually there, because there can be many other things, right? Not only exactly magnesium carbonate, there might be some other things in the antacid. So 3.5 gram of sample, how much of this is magnesium carbonate out of this 3.5 gram? Now the reaction we see, we have to write the reaction, and we already know this is excess reactant and this is 1:2 reaction, right? It's 1:2 reaction. But here we see that it is 1:1 reaction as well. There's 1 mole of carbon dioxide will be produced if I use 1 mole of magnesium carbonate. So this is one we find, this is one key point in our investigation. Already we found the first point, that 1:1. So how many moles of magnesium carbon dioxide will be produced? Exact that amount or that mole of magnesium carbonate will be in that powder. So now we go and find out how much carbon dioxide can be produced from this from this. So here it says that 714 milliliter of carbon dioxide at this condition, 22 degrees centigrade and 101 kilopascal. So in this condition and kilopascal, from there we see that from the gas law, if we use the gas law, right? If we use the gas law, N equals PV RT. So for this carbon dioxide, we find out, we just use all this thing and find out that it is 0.0295 moles of carbon dioxide. Okay, And since it is 1:1 reaction, 1:1 reaction, it will be exactly same number of moles of magnesium carbonate, right? Same number of moles. So since we find the number of moles, we can find the gram of magnesium carbonate. And then this is 2.49 gram, because just multiply by the gram per mole. And it is 2.549 gram, but we use 3.50 total amount of the solution powder. So 2.49 out of 3.50 gram is how many percentage? So it's all together. I mean, from this percentage, it is, we see that it is 71.1%, right? 71.1% actually it is. All right. So water content, gravimetric analysis is used to find out the water content, and the water content we can find out from food, from any other organic material. We can find how much water is holding of this. So the process is, we take the sample, we weigh it, and then we weigh it, I mean, we note it down, the amount that we found. We heat the sample at 105, just a little bit over 100 degrees centigrade, to make sure that the water, all the water evaporates, because water boils, I mean, evaporates at 100, boils at 100 degrees centigrade, so it will be evaporated after that. So 105, 110 at this temperature. And then we take the sample out from the furnace or oven and put it in a vacuum desiccator, in a desiccator where there is no air can go in, or moisture from the air can go in and bind with the sample again. After it becomes cold, we weigh it. And then we do the process few times till we get a constant weight, right? Like we will do this step will be done many times, like 4 or 5 times. We will try to do and see that every time we bring out the sample from the furnace oven, keep in the desiccator, whether it is the weight changes from the previous step. If it is changes from the previous step, we have to do this process once again. If it does not change the previous state, that means that is already stable. So now we know that how much water was there. So for a soup, you see that there are 223 gram at the initial state. Second mass after heating was found 33, third, fourth, fourth. So this third and fourth, it shows that they are the same. The mass did not change, so we know that it stops here. There is no more water here to evaporate. So the mass of that thing in the soup, what the water percentage in the soup was 223 minus 24, right? Minus 24, so 198 gram was water inside the soup. So how many percent of it was it there? So these are the things that this is pretty much about first today's lecture, and the summaries are these. We understand the limiting reactant. We see how to balance and write the molecular and ionic equations, and we also saw that how do we find out the percent yield, purity through the gravimetric analysis, and all these things. So do you have any question? Let me check if anyone has any question. Chen Ming, the actual mass of product is the product you want? No, the actual mass of the product is the by the reaction that we got. I do not know what you mean by I want or not. By the, I did the reaction and I got the product. Okay, so that is the actual mass. and the theoretical mass is I calculate it on my paper with the pen, and I found that there is some what is the mass of the going to be. That is the theoretical mass, but actual is what I got in the lab, what I got. Okay, so is there any question? Any other question? When do we really use n equals mv over 1000? Is it when both m and v is given? The v will be given, but the mass probably the mass, yeah. Otherwise, both of them, I mean, if the both of the entities are not given, you cannot find it. If you have to use this n equals mv over 1000, then both m and v will be given. Okay, and 1000 is actually, you know how to convert it to from milliliter to liter, right? We divide by 1000, so it convert from milliliter to liter. That is that. Okay, so any other question? I wanted to do the tutorial, but I'm too dry to talk. So I think I will talk about the tutorial tomorrow after I talk about the lab. Otherwise, I will book for extra time maybe to go for the tutorial one. Sir, may I ask you for tutorial exercise? The tutorial exercise, that is what I have actually. It is already on the canvas. Please try to solve those. And if you want to solve more, you want to try more challenges, please go to the books that's already given in the unit outline, right? Go to that books, and then in the books there are the exercise chapter. Please try to solve out those. All right, is there any other question? Is there any other question? I'm going to stop this recording now.